Right now, somewhere in the universe, a massive star is collapsing. Its core is being crushed inward with a force so immense that nothing can stop it. Not the pressure of atoms, not the resistance of neutrons. According to our best theory of gravity, that matter keeps falling, crushing itself smaller and smaller until it reaches a point of infinite density. A point where the laws of physics themselves break down completely. This is called a singularity, and for decades, physicists have accepted it as what lies inside every black hole. But what if that's wrong? What if the collapse doesn't continue forever? What if something kicks in at the smallest possible scale and stops the fall? That something has a name. It's called a Planck star. And it might change everything we think we know about black holes. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it means a lot to me. Now, let's begin. Let's start with a star. Not a small, quiet star like our sun. I'm talking about a massive star. One that outweighs the sun by at least 8 times. Maybe 20 times. Maybe 30. These are the true titans of the cosmos. They dominate the regions of the galaxy where they live. They burn hotter, brighter, and more furiously than almost anything else in the universe. Our sun has a surface temperature of about 5,500 degrees Celsius. A massive star can burn 3 or 4 times hotter than that. And because of the way stellar luminosity works, a star 20 times heavier than the sun doesn't just shine 20 times brighter. It can shine tens of thousands of times brighter. If you placed one of these massive stars where our sun currently sits, the daylight on Earth wouldn't just be brighter, it would be blinding, overwhelming. The oceans would boil away. The atmosphere would be stripped. Nothing we know would survive. But massive stars pay a steep price for that brilliance. They burn through their fuel incredibly fast. Our sun will live for about 10 billion years in total. It's been burning steadily for roughly 4.6 billion years, and it still has another 5 billion left. It's a slow, reliable furnace, but a star 20 times the sun's mass might live for only about 10 million years. That sounds long by human standards, but cosmically, it's nothing. The universe is 13.8 billion years old. A massive star's entire lifetime is less than 1/10 of 1% of that. These stars live fast, they burn hot, and they die in ways that are among the most violent events in all of nature. It's those deaths that bring us to the deepest question in all of physics tonight. For most of its life, a star exists in a delicate balance. On one side, you have gravity. Gravity is constantly pulling all that mass inward, trying to crush the star down to the smallest possible volume. Every particle of matter in the star feels the gravitational pull of every other particle, and all of that force is directed toward the center. In a massive star, the gravitational pressure at the core is billions of times greater than atmospheric pressure on the surface of Earth. It's a force of compression so enormous that without something pushing back, the star would collapse in on itself almost instantly. On the other side, you have the energy generated by nuclear fusion. Deep in the star's core, where temperatures reach tens of millions of degrees and pressures are beyond anything we can recreate in a laboratory, hydrogen atoms are being slammed together with such force that they fuse into helium. This nuclear fusion releases enormous amounts of energy. That energy creates outward pressure, both radiation pressure from the flood of photons streaming outward and thermal pressure from the intensely heated gas. This outward pressure pushes back against gravity. It holds the star up, So you have a constant tug of war. Gravity pulling in, fusion pushing out. As long as these two forces remain balanced, the star is stable. It shines. It burns. It continues to exist. This equilibrium can last millions of years in a massive star, but it cannot last forever, because eventually the star begins to run out of fuel. And this is where the story takes a dark turn. A massive star doesn't simply burn hydrogen and stop. When the hydrogen in the core is exhausted, the core contracts slightly under its own gravity, because fusion is no longer pushing back hard enough. As it contracts, it heats up. And when it gets hot enough, a new fusion reaction ignites. The star begins fusing helium into carbon. It's found a new fuel source and it stabilizes again. Crisis averted, temporarily, but helium burns faster than hydrogen did. The helium runs out more quickly, and when it does, the same process repeats. The core contracts, heats up, and ignites yet another new reaction. Carbon fuses into neon, neon into oxygen, oxygen into silicon. Each new fuel burns faster than the last. Hydrogen fusion in the core might last millions of years. Helium fusion might last a few 100,000 years. Carbon fusion might last a few thousand years. Neon fusion lasts about a year. Oxygen fusion lasts a few months. And silicon fusion, the final stage, lasts about 1 day. Let me say that again because it really deserves to sink in. After millions of years of steadily working through one nuclear fuel after another, the star reaches its final fuel and burns through it in a single day. 24 hours. One last burst, and then it's over. Because silicon fusion produces iron, and iron is different from every element that came before it in a way that seals the star's fate. Every previous fusion reaction, from hydrogen into helium, all the way through to silicon into iron, released energy. That released energy is what kept the star alive. But iron sits at the very peak of what physicists call the nuclear binding energy curve. It is the most tightly bound nucleus. Fusing iron doesn't release energy. It absorbs energy. It takes energy away from the star instead of giving it back. Iron is the dead end of nuclear fusion. There is nowhere left to go. So when the core fills up with iron, fusion stops. The engine that held the star up against gravity for millions of years simply shuts off. And gravity, which has been pulling inward the entire time, waiting patiently and relentlessly, finally wins the tug of war. What happens next takes less than 1 second. The iron core, suddenly unsupported by the outward force of fusion, collapses in on itself. The material falls inward at speeds reaching 70,000 kilometers per second. That's roughly a quarter of the speed of light. A core that was roughly the size of Earth gets compressed down to a ball about 20 kilometers across in a fraction of a second. The density reaches almost unimaginable levels. A single teaspoon of this compressed material would weigh about 4 billion tons. If you could somehow scoop out a teaspoon and drop it on the surface of Earth, it would weigh more than every building in a major city combined. At these densities, the very structure of atoms is destroyed. Electrons are crushed into protons, merging to form neutrons and releasing a flood of nearly massless particles called neutrinos. The core transforms into a solid ball of neutrons, packed together more tightly than anything we've ever encountered. This is what we call a neutron star. And here, for a brief moment, the collapse stops. The neutrons resist further compression because of a quantum mechanical effect called neutron degeneracy pressure. This is related to a principle described by the physicist Wolfgang Pauli in the 1920s, called the Pauli exclusion principle. This principle says that certain types of particles, called fermions, cannot exist in the same quantum state at the same time and place. Neutrons are fermions, so as they're squeezed more and more tightly together, they resist. They push back. Not because of any traditional force like electromagnetism. It's a quantum mechanical limit on how tightly identical fermions can be packed. And at neutron star densities, this quantum pressure is extraordinarily strong. Strong enough to halt the infall of an entire stellar core. When the outer layers of the dying star, still falling inward at a quarter of the speed of light, slam into this suddenly rigid core of neutrons, they bounce. That rebound generates a shock wave that travels outward through the rest of the star. The shock, amplified by the enormous flood of neutrinos streaming from the core, tears the star apart from the inside out. This is a supernova, one of the most powerful events in the known universe. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The energy released is more than our sun will produce over its entire 10 billion year lifetime, concentrated into a matter of seconds. The remnants of these explosions are among the most beautiful objects in the night sky. The Crab Nebula, for instance, is the still expanding debris cloud from a supernova that was observed by Chinese and Japanese astronomers in the year 1054. Nearly 1,000 years later, the wreckage is still glowing, still spreading outward, a ghostly monument to a star that destroyed itself. At the very center of the Crab Nebula sits a neutron star, spinning 30 times per second. The compressed core of the original star, still pulsing with energy almost a millennium after the explosion. The explosion scatters the star's outer layers across space, seeding the surrounding gas with heavy elements: carbon, oxygen, iron, gold, uranium. Every element heavier than hydrogen and helium was forged inside massive stars like this and flung outward by their deaths. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was created in the heart of a star that died long before our sun was born. You were made of stardust, literally, made from the ashes of a dead star, recycled across billions of years into the atoms that became you. After the supernova fades and the debris clears, what's left behind at the center depends on the mass of the original star. If the surviving core has a mass less than about 2 to 3 times the mass of our sun, neutron degeneracy pressure is strong enough to support it permanently. You get a stable neutron star, an object about 20 kilometers across with more mass than the entire sun, spinning rapidly, sometimes hundreds of times per second, shooting beams of radiation from its magnetic poles like a cosmic lighthouse. We've observed thousands of neutron stars. They are real, confirmed objects. They're among the most extreme things in the known universe, but they are stable. They can exist for billions of years without changing. But what if the remaining core is heavier than that? What if the gravitational compression is simply too much for even neutron degeneracy pressure to resist? This is where we enter some of the most fascinating and deeply troubling territory in all of physics. If the collapsing core exceeds a critical mass, roughly 2 to 3 solar masses, then nothing known in physics can stop what comes next. Neutron degeneracy pressure fails. There is no other known force, no known mechanism, no known physical phenomenon anywhere in established science that can resist gravity at this point. The collapse continues, and nothing stops it. According to Einstein's general theory of relativity, published in 1915, That collapse doesn't just continue for a while and then find a new equilibrium. It continues all the way down to zero volume, to infinite density. The matter falls inward, past every conceivable resistance, until the entire mass is concentrated at a single mathematical point. A point called a singularity. A point where the density is infinite, the curvature of space-time is infinite, and the known laws of physics simply break down. They stop giving meaningful answers. But before we talk about what might replace the singularity, let's look at the other prediction general relativity makes during this collapse, the event horizon. Because understanding the event horizon is crucial to understanding everything that comes next. As the core collapses and its density increases, at some point the mass becomes concentrated in a small enough region that the escape velocity from its surface reaches the speed of light. This critical radius was first described mathematically by the German physicist and astronomer Karl Schwarzschild, who found an exact solution to Einstein's field equations in 1916, just months after general relativity was published. He did this while serving on the Eastern Front of the First World War, which makes the achievement even more remarkable. At the Schwarzschild radius, a boundary forms. This boundary is the event horizon, and it represents something extraordinary. Beyond this line, nothing can escape. Not matter, not light, not radiation, not information of any kind. If you were falling towards a black hole and crossed the event horizon, you would notice nothing unusual at that moment. There's no wall, no barrier, no physical surface. Space-time is smooth and continuous at the horizon, but you would never be able to return. The curvature of space-time beyond the event horizon is so extreme that all paths, every possible direction you could travel in, including the direction of light itself, curve inward toward the center. Moving outward becomes as impossible as moving backward in time. You are trapped, inevitably drawn inward toward whatever lies at the center. From outside the event horizon, nothing that crosses it can ever be seen again. Information goes in, but never comes out. The event horizon is a one-way door in the fabric of space-time. Now, the idea of gravitational collapse and singularities has a complicated history. The concept of objects so massive that light cannot escape goes back centuries. As early as 1783, an English natural philosopher named John Michell realized that a sufficiently massive and dense object would have an escape velocity exceeding the speed of light. In 1796, the French mathematician Pierre-Simon Laplace independently reached the same conclusion. But their reasoning used Newtonian gravity, and when the wave theory of light became dominant in the 1800s, these ideas were largely forgotten. General relativity brought the idea roaring back, but for decades, most physicists, including Einstein himself, refused to accept that singularities could actually form in nature. Einstein published a paper in 1939, specifically arguing against it. He believed nature would find some mechanism to prevent such extreme collapse. The singularity was, in his view, a mathematical quirk of the equations, not something that could physically exist. Yet in that very same year, 1939, the American physicists J. Robert Oppenheimer and Hartland Snyder published a paper showing that Einstein's own equations predicted exactly this outcome. Using general relativity, they demonstrated mathematically that a sufficiently massive star, once it exhausted its fuel, would collapse through the event horizon and continue falling toward a singularity. Their calculation assumed an idealized, perfectly spherical star with no rotation, but it was mathematically rigorous, and it was deeply unsettling. Many physicists held out hope that this was a consequence of the idealization. Maybe real stars, with their rotation, asymmetries, and internal turbulence, would behave differently. Maybe the messiness of reality would prevent the singularity from forming. This hope persisted for over 2 decades. Then, in 1965, the British mathematician and physicist Roger Penrose destroyed that hope. Penrose proved what is now called the Penrose singularity theorem. What he showed was devastating for anyone still hoping singularities were just mathematical artifacts. Under very general conditions that apply to any realistic collapse, once a trapped surface forms, meaning once enough mass is squeezed into a small enough region that even light cannot escape, a singularity must form inside. Not might form, must form. This result did not depend on the collapsing star being perfectly spherical. It didn't require the absence of rotation or pressure. It was a general theorem that applied to messy, realistic, imperfect collapse scenarios. As long as gravity is attractive, as long as matter has positive energy, and as long as certain very reasonable conditions about the structure of space-time hold, singularities are inevitable. Penrose received the Nobel Prize in Physics in 2020 for this contribution. Along with extensions developed in collaboration with Stephen Hawking in the late 1960s, the singularity theorems showed that singularities are not exotic anomalies. They are a core prediction of general relativity whenever enough mass collapses into a small enough space. For decades, the entire concept had lacked a proper name. Physicists awkwardly referred to these hypothetical collapsed objects as frozen stars, or gravitationally completely collapsed objects. The terminology was clumsy, and the concepts remained on the fringe of mainstream physics. Many researchers simply avoided the subject altogether. The idea of infinite collapse seemed too extreme, too troubling, and too disconnected from anything observable to be worth serious attention. That changed largely because of one person. In 1967, the American physicist John Wheeler gave the concept a name that would stick. During a talk at a conference, Wheeler used the phrase black hole. He didn't invent it. The phrase had appeared in print a few years earlier in a popular science article. But Wheeler, who was one of the most respected physicists in the world at the time, popularized it. He used it repeatedly in lectures and papers, and the name was perfect. 2 simple words that immediately conveyed the essential nature of the object. Black, because no light can escape. Hole, because anything that falls in cannot get back out. The name captured the imagination of physicists and the public alike. Before Wheeler gave them a name, collapsed objects were an obscure theoretical curiosity. After he named them, black holes became one of the most famous concepts in all of science. Sometimes naming something is the first step toward taking it seriously. And once physicists started taking black holes seriously, the field exploded. Within a decade, theorists proved that a black hole can be completely described by just 3 properties: its mass, its electric charge, and how fast it spins. Nothing else. No memory of the star that formed it. This stunning simplicity made black holes irresistible to physicists, and set the stage for the observational breakthroughs that followed. And we know that this collapse actually occurs in nature. We have observational evidence, powerful evidence from multiple independent sources. Let me walk through that evidence because it's important to understand just how solid the case for black holes has become. The most visually stunning confirmation came in 2019 when the Event Horizon Telescope collaboration released an image that went around the world. It showed a glowing ring of superheated gas surrounding a dark central shadow. That shadow was the event horizon of a supermassive black hole at the center of galaxy Messier 87, located about 55 million light-years from Earth. The black hole has a mass of roughly 6.5 billion times the mass of our Sun. The image wasn't taken by a single telescope. It was constructed from data gathered by a network of radio telescopes spread across the entire planet, from Hawaii to Spain to Antarctica, all synchronized to observe the same object at the same time. The result was effectively an Earth-sized telescope with enough resolution to read a newspaper in New York from a cafe in Paris. 3 years later, in 2022, the same collaboration released an image of the black hole at the center of our own galaxy, Sagittarius E star. This one is much closer, about 26,000 light-years away, and much smaller, only about 4 million solar masses. But the image confirmed what decades of indirect evidence had already strongly suggested. There is a supermassive black hole at the heart of the Milky Way. That indirect evidence came largely from tracking stars near the galactic center. For over 2 decades, 2 independent teams, one led by Andrea Ghez at UCLA and the other by Reinhard Genzel at the Max Planck Institute in Germany, painstakingly tracked the orbits of stars circling an invisible point at the center of our galaxy. One star, designated S2, completes a full orbit in only about 16 years, whipping around at speeds exceeding 25 million kilometers per hour at its closest approach. The orbits of these stars allowed astronomers to calculate the mass and size of the invisible object they were orbiting. The result was clear. 4 million solar masses compressed into a region smaller than our solar system. The only known object that can pack that much mass into that small A space is a black hole. Ghez and Genzel shared the Nobel Prize in Physics in 2020 for this work, alongside Roger Penrose. And then there are gravitational waves. In 2015, the LIGO Observatory detected ripples in the fabric of space-time itself, produced when 2 black holes, each about 30 times the mass of the Sun, spiraled into each other and merged roughly 1.3 billion light-years away. The signal matched the predictions of general relativity with extraordinary precision. Since that first detection, LIGO and its partner observatories have detected dozens more black hole mergers. Each one confirms that black holes exist, that they behave exactly as general relativity predicts, and that they merge in ways that produce detectable gravitational waves. So, the existence of black holes is not in doubt. They are among the most well-confirmed objects in modern astrophysics. We've imaged their shadows, we've tracked stars orbiting them, we've heard the space-time vibrations they produce when they collide. The question is not whether black holes exist. The question is what lies inside them. But this confirmed reality makes the singularity problem more urgent, not less. Because here is the uncomfortable truth. A singularity, a point of truly infinite density and zero volume, is not really a physical prediction. It is a confession. It's the theory raising its hands and admitting that it doesn't know what happens next. Throughout the entire history of physics, whenever a theory has produced an infinity, whenever the math has given a nonsensical answer, it has meant one thing. The theory has been pushed beyond the domain where it applies. It's encountering physics it was never designed to describe. And this has happened before. The pattern is remarkably consistent. In the late 1800s, physicists studying how hot objects radiate energy ran into a devastating problem. Classical physics, using what was known as the Rayleigh-Jeans law, predicted that a heated body should emit increasing amounts of energy at shorter and shorter wavelengths. Push the calculation to its logical conclusion into the ultraviolet and beyond, and the prediction becomes absurd. Infinite energy. A simple heated oven, according to the best physics of the day, should radiate an infinite amount of energy at high frequencies. This was obviously spectacularly wrong. No oven emits infinite energy. The prediction was called the ultraviolet catastrophe, and it exposed a fundamental flaw in the classical understanding of radiation. The resolution came in 1900 from the German physicist Max Planck. Planck proposed something revolutionary. He suggested that energy is not emitted in smooth, continuous amounts as everyone had assumed. Instead, it comes in tiny, indivisible packets, which he called quanta. When he applied this single idea to the radiation equations, the infinity vanished. The prediction became finite, and it matched what experiments actually measured with extraordinary precision. The ultraviolet catastrophe wasn't a real catastrophe at all. It was classical physics encountering a regime where it simply didn't apply. And the solution wasn't to fix the old theory, it was to discover a deeper one: quantum mechanics. The same pattern appeared with the atom. Classical electromagnetic theory predicted that an electron orbiting an atomic nucleus should continuously radiate energy, lose speed, spiral inward, and crash into the nucleus in a tiny fraction of a second. Atoms, according to classical physics, should be catastrophically unstable. They should not exist. Yet atoms make up everything around you. The chair you're sitting in, the air you're breathing, your own body. The solution, again, was quantum mechanics. Electrons don't orbit nuclei the way planets orbit stars. They exist in quantized energy states with a minimum energy level, a ground state, below which they cannot fall. The catastrophe was resolved by new physics at a deeper level. Every major infinity in the history of physics has been a signal. Not a signal that something infinite actually exists, but a signal that the current theory is incomplete, that something is missing. That deeper physics is waiting to be discovered. Every single time physicists encountered an infinity, they eventually found new physics that resolved it. And this is exactly what most physicists believe about the singularity inside a black hole. General relativity is one of the most thoroughly tested and spectacularly successful theories in all of science. It has passed every experimental test thrown at it for over a century, but it is a classical theory. It treats space-time as perfectly smooth and infinitely divisible. It does not incorporate quantum mechanics. And at the extreme conditions deep inside a collapsing star, at densities far beyond anything we have ever measured or tested, quantum effects simply cannot be ignored. General relativity, for all its brilliance, is expected to break down in this regime, just as classical physics broke down when pushed to atomic scales or to high-frequency radiation. The singularity is not telling us what really happens at the center of a black hole. It's telling us that general relativity has reached its limit. That somewhere during the collapse, at some unimaginably high density, new physics takes over. Physics that unites gravity with the quantum world. A theory physicists call quantum gravity. So here is the question that drives everything we're going to explore tonight. What if the singularity is not real? What if the collapse does not continue all the way to infinite density? What if At some incredibly small but finite scale, something stops the fall. Some quantum gravitational effect that general relativity is blind to because it simply lacks the tools to describe it. What would that mean? What would happen to the collapsing matter if something intervened before it reached a singularity? What would exist at the center of a black hole instead of a point of infinite density? Some physicists have proposed an answer. They call it a Planck star. Not a star in the ordinary sense, not a glowing ball of fusing hydrogen. Something far stranger, far smaller, and far more profound. Something that exists at the very smallest meaningful scale in all of physics. A scale built from the most fundamental constants of nature. To understand what a Planck star might be, and why some physicists believe it could resolve the singularity problem, we first need to understand that scale. The scale where quantum gravity is expected to take over. The most extreme frontier in all of physics. It's called the Planck scale, and that's where we're headed next. To understand what might actually stop the collapse inside a black hole, we need to go to the smallest scale in all of physics. This is the Planck scale, and it is, without exaggeration, the most extreme frontier that science has ever confronted. Not because it involves enormous energies or vast distances, but because it involves the very opposite. Distances and volumes so impossibly tiny that the fabric of space-time itself might break down there. The Planck scale is where the two greatest pillars of modern physics, general relativity and quantum mechanics, collide head-on. And to understand why that collision matters for what happens inside a black hole, we need to understand each pillar individually, and then see why putting them together at these tiny scales is one of the hardest problems humans have ever faced. Let's start with what the Planck scale actually is. In 1899, 1 year before his revolutionary discovery that energy comes in discrete packets, Max Planck noticed something remarkable. He found that you could combine three of the most fundamental constants in nature: the speed of light, Newton's gravitational constant, and the quantum of action that now bears his name, Planck's constant. And from these three constants alone, you could build a set of natural units. Not units chosen by human convention, like meters or seconds, but units that emerge from the fabric of physics itself. Units that any intelligent civilization anywhere in the universe, working from the same laws of physics, would inevitably discover. These are called Planck units, and there are several of them. They include a length, a time, a mass, a temperature, and a density. Each one is built from the same three fundamental constants, just combined in different ways. And each one represents a scale where quantum mechanics and gravity become equally important. A scale where neither theory can be ignored, and where both must work together. Let's look at the most important ones for our story. The Planck length is approximately 1.6 times 10 to the minus 35 meters. That is an almost absurdly small number, but let me try to make it tangible for you. Imagine taking a single proton, one of the tiny particles in the nucleus of an atom. A proton is already incredibly small. You could line up roughly 1 trillion protons across the width of a single grain of sand. The proton is roughly 10 to the minus 15 meters across. The Planck length is 20 orders of magnitude smaller than that. 20 powers of 10. If you shrunk a proton down by the same factor that separates a proton from a grain of sand, you still wouldn't be at the Planck length. You'd need to shrink it down far, far more. The Planck length is to a proton what a proton is to something roughly the size of a small city. It's a scale so far below anything we've ever directly measured that it challenges our ability to even conceive of it. And yet, physicists have strong theoretical reasons to believe that this scale is physically meaningful, that something genuinely important happens at this length, that space-time itself might change character here in ways that our current theories simply cannot describe. The Planck mass is quite different from what you might expect. It's about 22 micrograms. That might surprise you. 22 micrograms is tiny by everyday standards, roughly the mass of a grain of sand or a small flea egg. But by the standards of particle physics, it's enormous. The Planck mass is about 10 to the 19th times heavier than a proton. In a field where particles are measured in fractions of a proton mass, the Planck mass is extraordinarily large. It represents the mass scale at which the gravitational energy of a particle becomes comparable to its quantum energy. Below this mass, quantum effects dominate and gravity is negligible. Above it, gravity becomes the dominant force. The Planck mass sits at the crossover point. Now here is a critical distinction that gets confused surprisingly often, and it matters enormously for understanding Planck stars. The Planck density is not the same as the Planck mass. The Planck density is what you get when you compress a Planck mass of matter into a volume defined by the Planck length. It's the density you reach when quantum gravitational effects are expected to become dominant everywhere inside that volume. The Planck density is approximately 5 times 10 to the 96 kilograms per cubic meter. Let me try to put that in perspective, even though the number is so large it almost resists analogy. Take a neutron star. A neutron star is already the densest stable object we know of. A teaspoon of neutron star material weighs roughly 4 billion tons. The Planck density is about 10 to the 78 times denser than that. That's 10 followed by 78 zeros times denser than the densest stable object in the known universe. If you could somehow compress the entire sun, all of its mass, into a volume smaller than a single atomic nucleus, the density you'd achieve would still be more than 1 billion trillion times less than the Planck density. The Planck density is a regime so far beyond anything we've ever encountered that it makes even neutron stars seem fluffy and diffuse by comparison. These three quantities, the Planck length, the Planck mass, and the Planck density, are different things. They describe different aspects of the same fundamental threshold. The Planck length is about how small. The Planck mass is about how much mass triggers the crossover between quantum and gravitational dominance. The Planck density is about how concentrated. They are related because they're built from the same three constants, but they are not interchangeable. And the reason all of this matters is that the Planck scale is where general relativity and quantum mechanics are expected to collide. To understand why, you need to understand what each of these theories says about the world, and why they are, at a fundamental level, deeply incompatible. General relativity, Einstein's theory of gravity published in 1915, describes gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy bend space-time. Objects moving through that curved space-time follow the straightest possible paths. Paths that look curved to us because the space itself is curved. Earth doesn't orbit the sun because a force is pulling it. Earth follows the natural curvature of space-time created by the sun's mass. The key insight of general relativity is that space-time is dynamic. It's not a fixed stage on which physics plays out. It's part of the physics. Space-time bends, stretches, warps, and even ripples. And in general relativity, space-time is perfectly smooth. It's a continuous fabric. You can always zoom in further. There is no smallest piece of space-time in the theory. No matter how closely you look, space-time remains smooth, like a perfectly polished surface with no texture, no graininess, no minimum scale. Quantum mechanics, developed in the 1920s and 1930s, describes the behavior of matter and energy at atomic and subatomic scales. It reveals a world fundamentally different from the smooth, deterministic world of general relativity. In quantum mechanics, physical quantities come in discrete units. Energy is quantized. Angular momentum is quantized. Particles exhibit wave-like behavior, and there is a fundamental limit to how precisely you can know certain pairs of properties simultaneously, described by Heisenberg's uncertainty principle. You cannot know a particle's position and its momentum with perfect precision at the same time. The more accurately you pin down one, the fuzzier the other becomes. This isn't a limitation of our instruments. It's a fundamental feature of nature itself. Quantum mechanics has been tested to extraordinary precision. Its predictions agree with experiments to more decimal places than any other theory in the history of science. The calculations of quantum electrodynamics, for example, match experimental measurements to better than 1 part in 10 billion. Richard Feynman once compared this to predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. Quantum mechanics works. It describes the behavior of atoms, molecules, photons, electrons, and all the fundamental forces except gravity with astonishing accuracy. General relativity also works. It predicts the bending of light around massive objects, the slowing of time in gravitational fields, the existence of gravitational waves, and the behavior of black holes. It has passed every experimental test ever devised. The problem is that these two theories describe nature in fundamentally contradictory ways. General relativity says space-time is smooth and continuous. Quantum mechanics says physical quantities are discrete and granular. General relativity is deterministic at its core. If you know the state of space-time at one moment, you can predict its state at any future moment. Quantum mechanics is fundamentally probabilistic. You can only predict the probability of different outcomes, not which specific outcome will occur. When the effects of both theories are small, this contradiction doesn't matter. At everyday scales, gravity is so weak and objects are so large that quantum effects are negligible for gravitational physics. At atomic scales, where quantum mechanics dominates, gravitational forces between individual particles are so vanishingly weak that they can be completely ignored. In our daily experience, the two theories never need to talk to each other. They govern different realms. But at the Planck scale, there is no escape. Inside a collapsing star, as matter approaches the densities predicted near a singularity, both quantum effects and gravitational effects become overwhelmingly strong simultaneously. Gravity is extreme because the curvature of space-time is enormous. Quantum effects are extreme because the matter is being compressed into volumes approaching the Planck length. You cannot ignore either theory, you need both, and yet, when you try to combine them using the standard mathematical techniques that work brilliantly everywhere else in physics, the result is catastrophic. The equations produce infinities, not elegant, removable infinities like the ones physicists encounter in quantum electrodynamics, where clever mathematical techniques can sweep them away. These are deep, stubborn, uncontrollable infinities that resist every attempt to eliminate them. The theory breaks down completely. It gives no answers at all. This is the problem of quantum gravity, and it has resisted solution for the better part of a century. Einstein spent the last 3 decades of his life searching for a unified theory and never found one. Some of the greatest minds in physics have worked on this problem since the 1940s, and no one has definitively solved it. But that doesn't mean no progress has been made. Several approaches to quantum gravity have been proposed, each with strengths and weaknesses, each offering a different picture of what space-time might look like at the Planck scale. And the one most relevant to the Planck star proposal is called loop quantum gravity. Loop quantum gravity was developed beginning in the 1980s and 1990s. Its foundations were laid by several physicists, including Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, among others. It takes a fundamentally different approach from some other quantum gravity proposals. Instead of adding new ingredients to nature, instead of proposing extra dimensions or new kinds of particles or strings, loop quantum gravity takes the core principles of general relativity and applies the rules of quantum mechanics directly to space-time itself. Here is the key idea, and it's one of the most profound concepts in all of theoretical physics. In loop quantum gravity, space is not infinitely divisible. General relativity treats space-time as a smooth, continuous fabric that you can divide into smaller and smaller pieces forever. Loop quantum gravity says no. When you apply quantum mechanics to the geometry of space itself, treating the geometry as a quantum object just like you treat the energy of an atom as a quantum object, you discover that geometric quantities like area and volume come in discrete chunks. There is a smallest meaningful area. There is a smallest meaningful volume. You cannot have a piece of space smaller than this minimum. Space has a granular structure at the Planck scale. This is not like the graininess of a photograph where you zoom in and eventually see individual pixels. It's more fundamental than that. In a digital photograph, the pixels exist on a smooth underlying screen. The graininess is imposed on top of something continuous. In loop quantum gravity, the graininess is the space itself. There is no smooth background underneath. The discrete chunks of volume are the fundamental building blocks from which space is woven. The mathematical structure that describes this quantum geometry is intricate and beautiful. Space is represented by what physicists call spin networks, graphs whose edges carry quantum numbers that encode the areas and volumes of tiny chunks of space. As these networks evolve over time, they form structures called spin foams. These mathematical objects replace the smooth space-time of general relativity with a discrete quantum geometry that has a minimum scale, the Planck scale. Now, why does any of this matter for black holes? Because this discreteness of space, this minimum volume, creates something that has no counterpart in classical physics. It creates a natural resistance to unlimited compression. Think about it this way. In general relativity, where space is perfectly smooth and infinitely divisible, there is no flaw. Matter can always be compressed further. There's always more room, so to speak, because you can always divide space into smaller pieces. The collapse can continue without limit, all the way to zero volume and infinite density. Nothing in the theory prevents it. But in loop quantum gravity, there is a flaw. Space has a minimum volume element. You cannot compress matter below this scale because there is no space smaller than this. As matter approaches the Planck density, it encounters this fundamental graininess, and the quantum geometry pushes back. This resistance isn't like the degeneracy pressure that holds up neutron stars. That pressure comes from quantum properties of matter, specifically the Pauli exclusion principle acting on fermions. The resistance that loop quantum gravity predicts comes from quantum properties of space itself. The geometry of space-time becomes the source of the opposition to further collapse. It's not the matter that refuses to be compressed further. It's space itself that refuses to be made smaller. This is a genuinely new kind of physical effect. It exists only at the Planck scale. At lower densities, at scales much larger than the Planck length, the discrete nature of space is completely invisible. The quantum chunks are so incredibly small that space-time looks perfectly smooth, just as general relativity describes. The corrections from loop quantum gravity are negligible. This is important because it means the theory doesn't contradict any of the experiments and observations that have confirmed general relativity. At the scales we can measure, the two theories agree. The differences only appear at the extreme conditions deep inside collapsing matter approaching the Planck density. This was demonstrated most convincingly in a simplified setting. In 2004, researchers applied the principles of loop quantum gravity to a cosmological model, studying the very early universe near the Big Bang. In classical general relativity, if you trace the expansion of the universe backward in time, you reach a point where all the matter and energy in the observable universe was compressed into a single point of infinite density, another singularity, just like the one inside a black hole. But when the researchers applied the quantum geometry of loop quantum gravity to this cosmological model, the singularity disappeared. Instead of infinite density, the universe reached the Planck density and then bounced. The collapse reversed. The infinite singularity of the Big Bang was replaced by a quantum bounce, a smooth transition from a contracting phase to an expanding phase. The density became very, very high, reaching the Planck density, but it never became infinite. The quantum geometry of space prevented it. This result is called loop quantum cosmology, and it's one of the most celebrated achievements of the loop quantum gravity program. Let me be clear about what this means and what it doesn't mean. Loop quantum cosmology is a simplified model. It doesn't prove that the full theory of loop quantum gravity is correct. It doesn't prove that the Big Bang was actually a bounce, but it demonstrates something crucial. It demonstrates that within this theoretical framework, singularities can be resolved. The quantum structure of space, the discreteness of geometry at the Planck scale, naturally prevents densities from reaching infinity. It provides a concrete mechanism for halting the collapse and replacing the singularity with a bounce. And if this mechanism works for the cosmological singularity, for the Big Bang, then maybe it also works for the singularity inside a black hole. That's the conceptual foundation of the Planck star proposal. The idea begins with the same observation that motivated loop quantum cosmology. General relativity predicts a singularity wherever matter collapses to infinite density. Loop quantum gravity introduces a quantum geometry that resists unlimited compression and replaces infinite density with a bounce at the Planck density. If this applies inside a black hole, then the collapsing matter does not reach a singularity. It falls inward. Its density increases enormously, far beyond nuclear densities, far beyond neutron star densities, approaching the Planck density. And then, at the Planck density, the quantum geometry of space kicks in. The discrete structure of space-time resists further compression, and the collapse halts, not gently, not gradually, it halts and reverses. The matter bounces. Now here's where you need to understand something crucial. The Planck density is not the same as the Planck length, even though both involve the Planck scale. When we say the collapse halts at the Planck density, we're not saying the matter is compressed to a single Planck length-sized point. The actual size of the region where the bounce occurs depends on how much mass is collapsing. For a stellar mass black hole, the matter at the moment of the bounce would occupy a region far larger than the Planck length. Still extraordinarily tiny by any human standard, but not as small as the Planck length itself. What reaches the Planck scale is the density, not necessarily the size. This distinction matters because it means a Planck star is not simply a point. It's a region of matter at an extreme but finite density, held in a state that exists only because of the quantum structure of space itself. This bouncing core, this incredibly dense but finite object hidden inside the event horizon, is what physicists Carlo Rovelli and Francesca Vidotto named a Planck star in 2014. The name is elegant but easy to misunderstand. It's not a star in the way our sun is a star. It's not fusing hydrogen. It's not glowing with thermal radiation. It's not sitting on a main sequence diagram. It's called a star because, like a star, it's a self-supporting object. A structure where an outward pressure balances an inward compression. But the pressure is not from nuclear fusion. It's from the quantum geometry of space-time itself. And the scale is not stellar. It's subnuclear, compressed into a volume far smaller than an atom. What makes this proposal so compelling is that it doesn't require any new exotic ingredients. It doesn't postulate new dimensions of space. It doesn't introduce new particles or new forces. It simply takes the principles of quantum mechanics and applies them to the geometry of space-time, as loop quantum gravity does, and traces the consequences for collapsing matter. The result is that the singularity predicted by general relativity is replaced by a bounce at the Planck density. The matter reaches an extreme but finite state and then rebounds. The comparison to earlier resolutions of infinities in physics is almost irresistible. Classical physics predicted infinite radiation from hot bodies. Quantum mechanics introduced discrete energy levels, and the infinity disappeared. Classical physics predicted unstable atoms. Quantum mechanics introduced quantized electron orbits, and atoms became stable. General relativity predicts infinite density inside black holes. Loop quantum gravity introduces discrete geometry, and the infinity might disappear too. The pattern is the same. A classical theory predicts an absurd infinity. A deeper quantum theory introduces discreteness at a fundamental scale. The infinity is resolved. Now, there's an important caveat here, and I want to be very upfront about it. Loop quantum gravity is not a complete, fully proven theory. It is a leading candidate for quantum gravity. Its mathematical structure is rigorous and internally consistent. It has produced impressive results in simplified settings, like loop quantum cosmology, but it has not been experimentally verified. No experiment has ever directly tested the predictions of loop quantum gravity. No observation has confirmed that space is discrete at the Planck scale. The Planck scale is so incredibly tiny, so far below anything our instruments can probe, that direct experimental tests are extraordinarily difficult, perhaps impossible, with any technology we can currently imagine. Other approaches to quantum gravity exist. String theory proposes that the fundamental constituents of nature are not point particles, but tiny vibrating strings, and it offers its own approach to resolving singularities. Asymptotic safety suggests that gravity might become well-behaved at high energies without requiring new structures at all. These are serious, well-developed programs with their own insights and predictions. The Planck star proposal comes specifically from the loop quantum gravity framework. It is not a consensus prediction of quantum gravity in general. It's a prediction of one particular approach. But the underlying logic is shared by many approaches. The idea that singularities are not real, that they signal the breakdown of classical physics rather than a genuine feature of nature, that quantum gravitational effects should halt the collapse at some finite density. This is widely accepted across the quantum gravity community. The specific mechanism might differ. Loop quantum gravity says discrete geometry halts the collapse. String theory might say something different about the interior structure, but the conviction that infinite density is unphysical, that something stops the fall, is remarkably common among theoretical physicists working on gravity. And if something does stop the fall, if the collapse halts at the Planck density and the matter bounces, then a series of extraordinary consequences follow. Consequences involving time, involving the nature of black holes, involving the relationship between black holes and their mysterious time-reversed counterparts called white holes. Consequences that might even resolve one of the deepest paradoxes in all of physics. The question of what happens to the information swallowed by a black hole. Those consequences are where we're going next, because the bounce itself, remarkable as it is only the beginning of the story. What happens after the bounce, and how it looks to observers watching from far away, is where the Planck star proposal becomes truly extraordinary. So the collapse halts. The matter inside the black hole, falling inward at tremendous speed, compressed to densities far beyond anything a neutron star could withstand, reaches the Planck density and stops. The quantum geometry of space-time, the granular structure of space predicted by loop quantum gravity, resists further compression. The infall decelerates, and then, remarkably, something happens that changes the entire picture. The matter doesn't just stop, it bounces back. Let's be very precise about what this means, because the word bounce might conjure images of a rubber ball hitting a floor and springing back. That's not quite what's happening here. When matter reaches the Planck density inside a collapsing star, it encounters a regime where the classical equations of general relativity no longer apply. The quantum corrections become so dominant that they reverse the effective force of gravity. In the standard picture, gravity is always attractive. Mass pulls mass inward. Space-time curvature drives matter toward greater and greater compression. But in the loop quantum gravity framework, when densities approach the Planck threshold, the quantum corrections flip the sign. What was attractive becomes repulsive. What was pulling inward begins pushing outward. The geometry of space-time itself generates an enormous outward pressure that overwhelms the inward pull of gravity. This is the bounce. Not a gentle rebound, but a violent reversal. The matter that was falling inward at a significant fraction of the speed of light is now being pushed outward by the quantum structure of space. The singularity that general relativity predicted, that point of infinite density, never forms. Instead, the matter reaches a maximum density, an incredibly high but finite density, the Planck density, and then the collapse reverses into an expansion. And this bouncing object, this transient state of matter held momentarily at the Planck density before rebounding outward, is what Carlo Rovelli and Francesca Vidotto called a Planck star. Now, I want to be very careful here because even though we covered what a Planck star isn't earlier, the name still creates a temptation to picture something visible, something you could point a telescope at. But a Planck star is a quantum gravitational state, not an object in any conventional sense. It is matter compressed to the Planck density, existing in a regime where the very distinction between space and matter becomes blurred. It is hidden deep inside the event horizon of what externally looks like a perfectly ordinary black hole. From the outside, looking at the black hole with any telescope or instrument we possess, you would see absolutely no difference. The event horizon would look the same. The gravitational field would behave the same. Every observable property of the black hole would be identical, whether a singularity sits at the center or a Planck star sits at the center. The difference is entirely internal. It's about what the theory predicts is happening inside, in the region we cannot directly observe. The Planck star exists at sizes that are incredibly tiny, but not zero. For a black hole with a mass comparable to our Sun, the Planck star at the moment of maximum compression would be far smaller than a proton, but far larger than the Planck length. It occupies a finite volume, it has a finite density, and it has a finite future, because it's not stable. It's a transient phenomenon. The matter hits maximum density, and then starts expanding outward again. The Planck star is a moment, not a permanent structure. But here is where the story becomes genuinely mind-bending. Because the bounce might happen very quickly for the matter itself, but the outside universe tells a completely different story. To understand this, you need to appreciate one of the most counterintuitive features of general relativity. Time is not absolute. Time does not flow at the same rate everywhere. The rate at which time passes depends on where you are and how strongly gravity is pulling on you. This isn't science fiction. It's measured fact. We've confirmed it with atomic clocks on airplanes, with GPS satellites in orbit, and with observations of distant stars. Time runs slower in stronger gravitational fields. The stronger the gravity, the more time slows down relative to someone far away. Near a black hole, this effect becomes extreme. Imagine you're watching a friend fall into a black hole from a safe distance. As your friend approaches the event horizon, you notice something strange. Their movements appear to slow down. Their clock, if you could somehow read it, ticks more and more slowly. The light they emit gets stretched to longer and longer wavelengths, shifting from visible light to infrared to microwave to radio waves. They appear to move in slow motion, and the closer they get to the event horizon, the more extreme the slowdown becomes. From your perspective, watching from far away, your friend never actually crosses the event horizon. They appear to freeze at the boundary, their image growing dimmer and redder as the light stretches to wavelengths too long to detect. They seem to hover there forever, slowing down asymptotically, never quite reaching the horizon. But from your friend's perspective, everything is completely different. They cross the event horizon without noticing anything unusual. No barrier, no wall, no flash of light. Nothing special happens at the horizon from their point of view. They continue falling inward, and depending on the size of the black hole, they reach the center in a remarkably short time. For a stellar mass black hole, the fall from the event horizon to the center takes only a tiny fraction of a second. For a supermassive black hole, it might take a few hours, but it's always finite. always fast. This enormous discrepancy between the experience of someone falling in and the observation of someone watching from far away is called gravitational time dilation, and it's absolutely central to understanding the Planck star proposal. Here is the key insight. When the collapsing matter inside a black hole reaches the Planck density and bounces, that bounce happens in the matter's own proper time. Proper time is the time experienced by the matter itself, the clock that travels with it. And in proper time, the bounce can be incredibly fast. The matter collapses, reaches maximum density, and rebounds almost instantaneously. From the perspective of the matter itself, the whole process might take a tiny fraction of a second. There is no long waiting period, no extended stay at extreme densities. The matter hits the Planck density and immediately springs back outward. But from the perspective of a distant observer, someone watching the black hole from far away, the situation is radically different. The extreme gravitational time dilation near the Planck star stretches what was a momentary event into something that appears to last an extraordinarily long time. How long? In the models proposed by Rovelli and Vidotto, the bounce that takes a fraction of a second in proper time could appear to take billions of years, or even longer, as seen by a distant observer. Let me try to make this more concrete with an analogy. Imagine you're watching a film of someone diving into a swimming pool, but the film has been slowed down, massively slowed down. From the diver's perspective, the whole experience takes about 1 second. They leave the board, arc through the air, enter the water, and surface on the other side. 1 second of experience time. But now imagine watching that same dive played back so slowly that it takes centuries to unfold. You see the diver leave the board, years pass, the diver is still arcing through the air, barely moving. Decades pass, the diver is still falling, inching toward the water surface. Centuries pass, the diver still hasn't entered the water. From your perspective as the viewer, the dive appears frozen. Almost nothing is happening. But from the diver's perspective, the whole thing already happened. They already hit the water, plunged in, and came back up. The event is over. It's just being played back at a speed so slow, it looks eternal. The Planck star bounce is something like this, but far more extreme. The time dilation isn't a playback effect, it's real. It's caused by the extreme curvature of space-time near the Planck density. The matter genuinely experiences a fast bounce. A distant observer genuinely measures an enormous elapsed time. Both experiences are real. Both are physically correct. There is no contradiction, just two different clocks running at unimaginably different rates because of the intensity of the gravitational field between them. Let me say that again, because it's one of the most startling features of this proposal. The matter bounces almost instantly in its own time frame. But because of the extreme curvature of space-time inside the event horizon, because of the enormous gravitational time dilation, that instantaneous bounce gets stretched from the outside perspective into some things that could last longer than the current age of the universe. This means that right now, if a Planck star exists inside every black hole, those bounces could be in progress. The matter collapsed, hit the Planck density, and bounced. From the matter's perspective, the bounce already happened. But from our perspective, looking at the black hole from across the galaxy, the bounce is still unfolding. It started billions of years ago and it hasn't finished yet, because the extreme time dilation makes the process appear almost frozen. This is not some new exotic physics being added to the picture. This is standard general relativity. Gravitational time dilation is one of the most well-tested predictions of Einstein's theory. What the Planck star proposal does is combine this well-understood effect with the quantum bounce predicted by loop quantum gravity. The quantum part is the bounce itself, the halting and reversal of the collapse at the Planck density. The classical part is the extreme time dilation that makes the bounce appear to take an enormous amount of time from the outside. Now, let's follow the matter through the bounce and see what happens next. Because the bounce doesn't just stop the collapse, it reverses it. The matter that was falling inward is now moving outward. And this outward moving matter brings us to one of the most mysterious and least understood objects in all of general relativity: the white hole. A white hole is essentially the time reverse of a black hole. If a black hole is a region of space-time where nothing can escape, a white hole is a region where nothing can enter. In a black hole, matter and light can cross the event horizon going inward, but can never come back out. In a white hole, matter and light come streaming outward from a central region, but nothing from outside can fall in. A black hole swallows, a white hole expels. White holes have been part of the mathematical landscape of general relativity since the 1960s. They appear naturally in the complete mathematical description of the Schwarzschild solution, the simplest black hole spacetime. When you extend the Schwarzschild geometry to its fullest mathematical form, you find not just a black hole region, but also a white hole region. They're two sides of the same mathematical coin. The equations that describe a black hole have a time reverse solution that describes a white hole, just as the equations governing a bouncing ball going up also describe the ball coming down. But for decades, most physicists dismissed white holes as purely mathematical curiosities. They exist in the equations, sure, but do they exist in nature? The standard view was no. Black holes form through gravitational collapse. Stars die, their cores collapse, and event horizons form. This is a physical process that we observe. But white holes didn't seem to have any physical origin. They appeared in the equations, but there was no known mechanism that could create one. They were considered mathematical artifacts, solutions to the equations that happened to be technically valid, but physically irrelevant, like a negative time solution to a motion equation, mathematically correct, but not describing anything real. To understand why physicists dismissed white holes for so long, it helps to think about what one would actually look like if you encountered it in nature. Imagine a region of space where matter and light are streaming outward from a central point. Not because something exploded there like a supernova, but because the very geometry of space-time in that region forbids anything from entering. You could fire a rocket directly at it, accelerate toward it at tremendous speed, and the curvature of space-time would deflect you away. You could shine a laser at it, and the light would bend around the boundary without ever crossing in. Things come out. Nothing goes in. It's the opposite of a black hole in every way. This sounds exotic, and it is, but the mathematical description of a white hole is exactly as rigorous as the description of a black hole. It comes from the same equations. When Carl Schwarzschild found a solution to Einstein's field equations back in 1916, the full mathematical structure of that solution contained both a black hole region and a white hole region. They weren't separate theories. They were two aspects of the same geometry, connected in the mathematical structure of the solution like two sides of an hourglass. The reason physicists treated white holes as fiction wasn't that the math was wrong, it was that no one could figure out how nature would create one. Black holes have a clear formation mechanism. Stars die and collapse, but white holes seem to require matter to already be inside them at the beginning of time, expanding outward forever with no explanation for how it got there. They violated the physicist's sense of physical reasonableness. The equations allowed them, but the universe didn't seem to need them. The Planck star proposal provides, for the first time, a physical mechanism that could produce a white hole. The mechanism is the bounce. Matter collapses inward, forming a black hole. It reaches the Planck density and bounces. The outward moving matter transforms the interior geometry from a black hole into a white hole. The white hole isn't eternal. It wasn't placed there at the beginning of time. It was created by the bounce. It's the second act of a story that began with gravitational collapse. And that changes the white hole from a mathematical curiosity into something that might actually occur in nature. Now, as the matter expands outward after the bounce, the geometry of space-time inside the event horizon begins to change. What was a black hole geometry, with all paths curving inward toward the center, gradually transforms into a white hole geometry, with all paths curving outward from the center. The trapping horizon, the boundary that defines the black hole, slowly shrinks as the bouncing matter pushes outward. Eventually, after an enormously long time, as measured by a distant observer, the black hole transitions completely into a white hole. The event horizon opens up. The trapped matter and energy burst outward. The black hole is gone, replaced by a white hole that releases everything that fell in. This is a remarkable picture. It suggests that black holes are not permanent. They are not eternal prisons from which nothing ever escapes. Instead, they are temporary states. Matter falls in, gets compressed to the Planck density, bounces, and eventually comes back out. The black hole phase is just one half of a longer process. The other half is the white hole phase, and the full process from collapse to bounce to release looks like a single event from the matter's perspective, but spans an enormous stretch of time as seen from the outside. One way to visualize this is to think of the black hole as a very slow explosion. The matter collapses inward, reaches maximum compression, and then explodes back outward. But the extreme gravitational time dilation makes this explosion appear to be frozen. From the outside, it looks like nothing is happening. The black hole just sits there, apparently unchanging, for billions of years. But internally the bounce has already occurred. The matter is already moving outward. It's just that the outward motion is so incredibly time dilated that it hasn't reached the event horizon yet. This brings us to one of the deepest problems in all of theoretical physics, a problem that the Planck star proposal was partly designed to address: the black hole information paradox. The information paradox was first identified in the 1970s by Stephen Hawking. In 1974 and 1975, Hawking made one of the most remarkable theoretical discoveries of the 20th century. He showed that black holes are not completely black. They emit radiation. Using the principles of quantum mechanics applied to the curved space-time near a black hole's event horizon, Hawking demonstrated that black holes slowly radiate particles and energy into space. This radiation, now called Hawking radiation, is incredibly faint. For a stellar mass black hole, it's far too weak to detect with any instrument we could build. But it's real, predicted by well-understood physics, and it has profound consequences. Here's why. As a black hole emits Hawking radiation, it loses energy. And because mass and energy are equivalent, as Einstein showed in 1905, Losing energy means losing mass. The black hole shrinks, slowly, incredibly slowly, but steadily. Over immense spans of time, a black hole evaporates. A stellar mass black hole would take roughly 10 to the 67 years to fully evaporate. That's far longer than the current age of the universe. But given enough time, the black hole will eventually vanish completely, leaving nothing behind but a faint glow of Hawking radiation. And this creates a devastating problem. Quantum mechanics has a fundamental rule: information cannot be destroyed. This isn't just a guideline or a preference, it's built into the mathematical structure of quantum mechanics at the deepest level. In quantum theory, the evolution of a physical system is described by something called a unitary operator. Unitarity means the process is reversible. If you know the final state of a system with perfect precision, you can, in principle, reconstruct its initial state. Information is preserved. It can be scrambled beyond recognition, mixed up and rearranged until it's practically impossible to recover, but it cannot be fundamentally erased. The information is always there, in principle, encoded somewhere in the system. What does information mean in this context? It doesn't mean words or data in the way we usually think of it. In physics, information means the complete, precise description of a system's quantum state. Every property of every particle, every spin, every charge, every momentum, every correlation between particles. Think of it this way. A diamond and a lump of charcoal are both made of carbon atoms. The same element, the same building blocks. What makes them different is how those atoms are arranged. That arrangement is information. If you could somehow record the exact quantum state of every atom in a diamond, you could in principle distinguish it from every other object in the universe. That quantum state is unique. It's a fingerprint. And quantum mechanics says that fingerprint can be scrambled, rearranged, and mixed up beyond all practical hope of recovery, but it can never be truly erased. The laws of physics always preserve enough structure that the original state could, in principle, be reconstructed. Now think about what happens when a black hole forms and then evaporates. A massive star collapses. It has a specific detailed quantum state, a precise description of every particle, every field, every degree of freedom. This information crosses the event horizon and falls into the black hole. Then, over unimaginably long time scales, the black hole evaporates through Hawking radiation. And here's the critical point. In Hawking's original calculation, the radiation emitted by the black hole is thermal. It's random. It carries no information about what fell in. The radiation from a black hole that swallowed a star looks identical to the radiation from a black hole that swallowed a giant cloud of gas of the same mass. The radiation doesn't encode the details of the infalling matter. It's like burning a book and claiming the smoke and ash contain all the information that was in the book. In principle, maybe, but in Hawking's calculation, the radiation appears to be truly random, not just scrambled. So when the black hole finishes evaporating, the information that fell in appears to be gone, destroyed, erased from the universe, and that violates the fundamental principle of unitarity, the bedrock of quantum mechanics. This is the information paradox. Either quantum mechanics is wrong about information preservation, or Hawking's calculation is incomplete in some way, or our understanding of black holes is missing something crucial. For decades, this paradox has generated enormous debate among physicists. Entire careers have been spent trying to resolve it. The Planck star proposal offers an elegant potential resolution. If a black hole doesn't end in a singularity, if the matter bounces at the Planck density and eventually transitions into a white hole, then information is never destroyed. It's not erased. It's temporarily trapped. The information that crossed the event horizon during the collapse is still there, inside the bouncing matter, preserved by the quantum state of the Planck star. It's locked away, inaccessible to outside observers for an extraordinarily long time because of gravitational time dilation, but it still exists. It hasn't been erased, it hasn't been destroyed, it's just been stored. And when the bounce completes, when the black hole transitions to a white hole and the event horizon opens, the information comes back out. It's released along with the matter that originally fell in. The information was never lost. It was just hidden for a very long time. This resolution is conceptually clean. It doesn't require modifying quantum mechanics. It doesn't require giving up unitarity. It doesn't require exotic new physics at the event horizon, like some other proposals suggest. All it requires is that the singularity is replaced by a bounce, which is exactly what loop quantum gravity predicts. The information paradox is resolved not by changing the rules, but by changing what happens at the center of the black hole. Replace the singularity with a Planck star, and the information has somewhere to go and a way to come back. However, there is a subtle complication. The timescale matters. In the Planck star picture, the bounce takes an enormous amount of time as seen from outside. For a stellar mass black hole, the time for the full transition from black hole to white hole might be comparable to the Hawking evaporation time, roughly 10 to the 67 years. During all that time, the black hole is also slowly losing mass through Hawking radiation. So there's a question about how these two processes interact. Does the black hole evaporate first, or does the bounce complete first? The answer depends on the details of the model and is still debated among physicists working in this area. Some calculations suggest that the bounce might complete around the same time the black hole has evaporated down to a very small size, when it has lost most of its mass through Hawking radiation. At that point, the remaining tiny black hole undergoes the final stage of the bounce, transitioning to a white hole and releasing whatever information and energy remain. This race between evaporation and bouncing is one of the most subtle and important aspects of the Planck star proposal, and it deserves careful attention. Because these two processes are fundamentally different in nature, and how they interact determines what the death of a black hole actually looks like. Hawking radiation is a quantum mechanical process that occurs at the event horizon. It's generated by the interplay between quantum fields and the curved space-time at the boundary of the black hole. It slowly nibbles away at the black hole from the outside, removing mass bit by bit over unimaginably long timescales. For a black hole of a few solar masses, the evaporation time is roughly 10 to the 67 years. That's a 1 followed by 67 zeros. To put that in perspective, the current age of the universe is only about 10 to the 10 years. The evaporation time is incomprehensibly longer than the universe has existed. The Planck star bounce, meanwhile, is happening on the inside. It's a quantum gravitational process occurring deep within the event horizon, driven by the discrete geometry of space-time at the Planck scale. In the matter's own proper time, the bounce is nearly instantaneous, but as seen from outside, the time dilation stretches it across an enormous span. The critical question is whether these two timescales, The evaporation time and the externally observed bounce time are comparable. If the bounce completes long before evaporation has had any significant effect, then the black hole essentially vomits its contents outward while still near its original mass. That would produce a very different signal than if the bounce completes only after the black hole has evaporated down to a tiny remnant. In the models developed by Rovelli and Vidotto, the two timescales appear to be roughly comparable for certain mass ranges. This is not a coincidence. In their framework, the bounce time scales with the mass in a way that naturally brings it into the same ballpark as the Hawking evaporation time. The result is that the bounce might complete precisely when the black hole has shrunk to a very small size, a microscopic remnant that then undergoes its final transition from black hole to white hole. This convergence of timescales is one of the more remarkable features of the proposal. It means the final moments of a black hole's life might be a quantum gravitational event, a burst of energy and information released as the last tiny remnant of the original black hole completes its bounce and transitions to a white hole. Not a slow fading, not a quiet death, a final flash. And that flash might be detectable. It might carry a specific observational signature, a fingerprint that could tell us whether Planck stars are real. Let me also address something that makes the Planck star proposal philosophically striking. In this picture, a black hole is not an end state. It's a process, a temporary phase in the life of matter. Matter falls in, gets compressed to an extreme but finite state, bounces, and eventually comes back out. The black hole is like a tunnel, not a dead end. Things go in and things eventually come out. The tunnel is just extraordinarily long from the outside perspective, stretched by gravitational time dilation into something that lasts longer than the current age of the universe. This transforms our understanding of what a black hole fundamentally is. In the classical picture, a black hole is a permanent feature of space-time. It forms and it persists forever, growing only when new matter falls in. The singularity at its center is an endpoint, a place where the story of the infalling matter simply ends. But in the Planck star picture, the story doesn't end. It continues through the bounce and back out. The black hole is not a conclusion, it's a chapter in a longer narrative, and the white hole that emerges at the end of the process is not some separate, exotic object. It's the same object, the same piece of space-time. The black hole and the white hole are two phases of a single phenomenon, connected by the Planck star bounce at the center. The black hole is the infall phase, the white hole is the release phase, and the Planck star is the turning point between them. This is an extraordinary reimagining of one of the most iconic objects in all of physics. Black holes have captured the human imagination for decades. They are symbols of mystery, of the unknown, of the limits of our understanding. The Planck star proposal doesn't diminish that mystery. If anything, it deepens it. It tells us that black holes might be even more remarkable than we thought. Not permanent prisons, but temporary cocoons. Containers that hold matter in an extreme state for unimaginably long periods, and then release it. Space-time structures that connect two phases of a single process, collapse and expansion, swallowing and releasing, linked by a quantum gravitational bounce at the most extreme density nature allows. But all of this, every part of this picture, remains theoretical. The bounce has not been observed. The Planck star has not been detected. The transition from black hole to white hole has not been confirmed. These are predictions of a specific theoretical framework, loop quantum gravity, applied to a specific physical scenario gravitational collapse. They are mathematically consistent. They are physically motivated. They resolve long-standing problems like the singularity and the information paradox. But they are not proven. And that raises the most important question of all. Can we test this? Is there any observation, any measurement, any experiment that could tell us whether Planck stars are real? Or are they destined to remain forever theoretical, forever hidden behind the event horizons of black holes, forever beyond our ability to confirm or refute? That's the question we need to answer next. So we have this extraordinary theoretical picture. A collapsing star reaches the Planck density inside its event horizon. The quantum geometry of space-time halts the infall. The matter bounces. The black hole eventually transitions into a white hole. Information is preserved, not destroyed. The singularity is avoided. It's elegant. It's physically motivated. It resolves some of the deepest problems in theoretical physics. But does it actually happen? This is the question that separates theoretical physics from established science. A beautiful theory that makes no testable predictions is philosophy, not physics. And the history of science is littered with beautiful ideas that turned out to be wrong. So the critical question for the Planck star proposal is whether it makes predictions that can, even in principle, be tested against observation. Whether there is anything we could look for in the sky, any signal, any signature, any fingerprint that would tell us Planck stars are real. The honest answer is that we don't currently have proof. No observation has confirmed a Planck star. No instrument has detected a signal that can only be explained by the Planck star bounce. But the story doesn't end there. Because physicists working on this proposal have identified several potential observational signatures, places where the Planck star hypothesis makes specific, testable predictions that differ from the predictions of other models. None of these has been confirmed yet, but they give us something to look for, and that's crucial. It means the idea is not permanently beyond the reach of experiment. It's just that the experiments are extraordinarily difficult. Let's start with the most direct prediction. If the Planck star picture is correct, then black holes are not permanent. They bounce. And the bounce, despite taking an enormous amount of time as measured by outside observers, does eventually complete. When it completes, the black hole transitions into a white hole and releases its contents. That final release should produce a burst of energy, a signal that could, in principle, be detected. The timing of this burst depends on the mass of the original black hole. More massive black holes have larger event horizons and stronger gravitational time dilation. Their bounces appear to take longer from the outside. A stellar mass black hole, one containing perhaps 10 solar masses, might take an almost unimaginably long time to complete its bounce, far longer than the current age of the universe. We would not expect to see any stellar mass Planck star bounces completing today. But what about much smaller black holes? General relativity doesn't set a minimum mass for black holes. In principle, a black hole could have any mass, even a very small one. And some cosmological models predict that in the very early universe, during the first fraction of a second after the Big Bang, conditions were extreme enough that tiny black holes could have formed. These are called primordial black holes. They wouldn't have formed through stellar collapse because no stars existed yet. They would have formed from the extreme density fluctuations present in the very early cosmos. Some of these primordial black holes might have had very small masses, perhaps comparable to the mass of a mountain or even less. And here's the key. Small black holes complete their bounces faster. The bounce time, as seen from outside, scales with the mass. A lower mass black hole has a smaller event horizon and weaker time dilation. The bounce completes sooner. For sufficiently small primordial black holes, the bounce time might be comparable to the current age of the universe, about 13.8 billion years. That means if these tiny primordial black holes formed in the first moments of the universe, some of them could be completing their bounces right now, today, in our sky. Rovelli, Vidotto, and other researchers have calculated what signal this final burst might produce when a small primordial black hole completes its transition from black hole to white hole. The energy released should emerge primarily as very high energy photons. Gamma rays. The specific energy of these gamma rays depends on the mass of the bouncing black hole and the details of the model, but the predictions point to a burst in a specific energy range. A short, sharp pulse of gamma ray radiation. This is an exciting prediction because we actually have instruments that detect gamma ray bursts. The Fermi Gamma Ray Space Telescope, launched in 2008, continuously monitors the sky for bursts of gamma radiation. Astronomers have catalogued thousands of gamma ray bursts of various types. Most of these have known astrophysical explanations. Long gamma ray bursts are associated with the deaths of massive stars. Short gamma ray bursts are associated with the mergers of neutron stars. But there are unexplained signals too. Bursts that don't fit neatly into either category. Could some of these be the signatures of Planck star bounces completing? The answer right now is that we don't know. The predicted signal from a Planck star bounce has specific characteristics, a particular energy spectrum, a particular duration, a particular spatial distribution that distinguish it from other astrophysical sources. But the signal would also be very faint. A single tiny primordial black hole completing its bounce would produce a burst far weaker than the gamma ray bursts we typically detect. We might need much more sensitive instruments to pick it up, or we might need to find a population of these events and detect them statistically, finding a pattern in the data rather than spotting a single dramatic event. There has also been speculation about a possible connection to fast radio bursts. Fast radio bursts are brief, intense pulses of radio emission that were first discovered in 2007. They last only milliseconds but release enormous amounts of energy. Most fast radio bursts are now thought to come from magnetars, highly magnetized neutron stars, but the phenomenon is still being actively studied. Some researchers have explored whether certain fast radio bursts might be connected to the final stages of Planck star bounces, where the released energy emerges at lower frequencies. This remains highly speculative. No fast radio burst has been convincingly linked to a Planck star. But the fact that researchers are looking, that they're making specific predictions and comparing them to observed data is significant. It means the Planck star hypothesis is making contact with observation, even if that contact hasn't yet produced a definitive result. Another potential observational avenue involves gravitational waves. When two black holes merge, they produce gravitational waves that we can detect with instruments like LIGO. The detailed shape of these gravitational wave signals depends on the internal structure of the merging objects. If black holes contain Planck stars instead of singularities, the gravitational wave signal might differ in subtle ways from the predictions of classical general relativity. These differences would be extremely small, probably far below the sensitivity of current detectors. But future gravitational wave observatories, including the planned space-based observatory LISA, might achieve the sensitivity needed to detect such differences. This is a long-term prospect, not something that will be resolved in the next few years, but it's a genuine observational pathway. Let me be very clear about the current state of evidence. As of now, there is no confirmed observational evidence for Planck stars. No gamma-ray signal has been identified as coming from a Planck star bounce. No fast radio burst has been conclusively linked to this process. No gravitational wave observation has revealed the internal structure of a black hole in a way that would confirm or deny the Planck star model. The proposal remains theoretical. It is a prediction of a specific quantum gravity framework applied to a specific physical scenario. It is well motivated, mathematically consistent, and physically compelling. But it is not proven. Now, to put the Planck star proposal in proper context, we need to compare it with other approaches to the same problem. Because loop quantum gravity is not the only framework that tackles the singularity inside black holes. Other approaches exist, and each offers a different picture of what might replace the singularity. Understanding these alternatives helps us see what's unique about the Planck star idea and what's shared across different approaches. The first major alternative comes from string theory, the other leading candidate for a theory of quantum gravity. In string theory, the fundamental constituents of nature are not point particles, but tiny one-dimensional vibrating strings. These strings exist in a space-time that might have more dimensions than the 4 we observe, 3 of space and 1 of time. The extra dimensions are curled up so small that we don't notice them in everyday life. String theory offers its own resolution to the black hole singularity problem. The most developed proposal is called the fuzzball model, originally pioneered by the physicist Samir Mathur, beginning around 2003. In the fuzzball picture, a black hole is not an empty region of curved space-time with a singularity at the center. Instead, the entire volume inside the event horizon is filled with a complex quantum state made of strings and higher dimensional objects called branes. There is no empty interior. There is no singularity. The black hole is, as the name suggests, a fuzzy ball of quantum string stuff that extends all the way to the event horizon. This is a radically different picture from the Planck star. In the Planck star model, the event horizon looks exactly like the classical prediction. The interior is mostly empty, with a tiny bouncing core at the center. In the fuzzball model, there is no mostly empty interior. The entire inside of the black hole is filled with quantum structure. The event horizon itself might have physical significance in the fuzzball picture, meaning that something unusual happens right at the boundary, not just deep in the interior. The fuzzball model also addresses the information paradox, but through a different mechanism. Because the quantum state of the fuzzball extends to the event horizon, the Hawking radiation emitted by the black hole is not truly random. It carries subtle correlations that encode the information about what fell in. Information leaks out gradually through the Hawking radiation, rather than being stored inside and released all at once when the black hole transitions to a white hole. The information is preserved, but the mechanism of preservation is completely different from the Planck star scenario. The second notable alternative is the firewall proposal. In 2012, 4 physicists, Ahmed Almeiri, Donald Marolf, Paul Chinsky, and James Sully, published a provocative paper arguing that the event horizon of a black hole might not be the smooth, featureless boundary that general relativity predicts. Instead, they argued that consistency requirements of quantum mechanics might force the event horizon to be a wall of extremely high energy radiation, a firewall that would destroy anything that crosses it. The firewall proposal was deliberately provocative. It was designed to highlight contradictions between different well-established principles of physics. If you insist that information is preserved during black hole evaporation, and if you insist that the laws of physics look normal for someone falling through the event horizon, and if you insist on other reasonable principles, you run into contradictions. The firewall argument says that something has to give, and one possibility is that the event horizon is not a smooth boundary, but a violent, destructive one. The firewall proposal differs dramatically from both the Planck star and the fuzzball. In the Planck star model, nothing unusual happens at the event horizon. The physics there is perfectly smooth. All the interesting quantum gravity effects happen deep inside, near the Planck density core. In the firewall proposal, the event horizon itself is where the drama occurs. A freely falling observer would be incinerated the moment they crossed the boundary. This contradicts one of the central principles of general relativity, the equivalence principle, which says that a freely falling observer should not experience anything unusual when crossing the horizon. Many physicists find this deeply troubling. The firewall debate has not been fully resolved. It highlighted genuine tensions in our understanding, but most physicists do not believe that firewalls actually exist. Instead, the firewall argument is seen as a sign that something deeper is going on, that our current frameworks are missing a crucial ingredient needed to consistently describe black hole horizons, interiors, and evaporation all at once. A third approach is called asymptotic safety. This idea, first proposed by Steven Weinberg in 1979 and developed further by Martin Reuter and others beginning in the late 1990s, takes a very different approach to quantum gravity. Instead of proposing new structures like loops or strings, asymptotic safety suggests that general relativity itself, with some quantum corrections, might be a complete and consistent quantum theory of gravity at all energy scales. The idea is that gravity becomes well-behaved at very high energies, instead of getting worse and worse as naive calculations suggest. If this is correct, then the singularity inside a black hole would be resolved not by new structures at the Planck scale, but by the smooth quantum corrections to gravity becoming dominant and preventing infinite densities. In the asymptotic safety picture, the interior of a black hole might look very different from the classical prediction, with quantum corrections softening the singularity into a region of high but finite curvature. Some calculations within this framework suggest outcomes similar to the Planck star bounce, a maximum density followed by a rebound, but through a different mechanism. Rather than discrete quantum geometry, it's the smooth running of gravitational coupling constants that prevents the singularity. So, what do all these approaches have in common? Despite their very different starting points, assumptions, and mathematical structures, all of them agree on one crucial point. The singularity is not real. Infinite density is not a physical outcome. Something, whether it's quantum geometry, string structure, fuzzballs, smooth quantum corrections, or something else entirely, prevents the collapse from reaching a true singularity. This near-universal agreement among quantum gravity researchers is significant. It's not just one framework saying singularities are unphysical. It's virtually every serious approach to the problem reaching the same conclusion through independent reasoning. The specific replacement for the singularity varies: a Planck star bounce, a fuzzball, a smoothed out region of high curvature. But the conclusion that infinite density doesn't actually occur is shared across the field. Where the approaches differ is in the details: what replaces the singularity, what happens at the event horizon, how information is preserved, whether the black hole eventually transitions to a white hole or evaporates through a modified form of Hawking radiation. These differences matter because they lead to different observational predictions. And it's through those observational predictions that we might eventually determine which approach, if any, is correct. But we need to be honest about how difficult this task is. The Planck scale is so incredibly far below anything our instruments can directly probe that testing these ideas experimentally is one of the greatest challenges in all of science. The Planck length is about 20 orders of magnitude smaller than a proton. Our most powerful particle accelerator, the Large Hadron Collider, probes distances down to about 10 to the minus 19 meters. The Planck length is 10 to the minus 35 meters. The gap between what we can probe and what we need to probe is 16 orders of magnitude. That's a factor of 10 quadrillion. Building an accelerator that could directly probe the Planck scale would require energies so enormous that the accelerator would need to be larger than the solar system. This is not a practical obstacle that better engineering will solve. It's a fundamental challenge. This means that direct experimental tests of Planck scale physics are almost certainly impossible with any foreseeable technology. We will probably never build an instrument that can directly observe the quantum structure of space-time at the Planck length. We will probably never directly see a Planck star. But indirect tests are possible, and this is where the observational signatures we discussed earlier become important. We might not be able to see a Planck star directly, but if Planck stars produce specific signals when they complete their bounces, signals that differ from the predictions of other models, then we might detect those signals. We might see the consequences of Planck stars even if we can never see the Planck stars themselves. This is how much of modern physics works. We never directly see quarks. We see the particles they produce when protons collide at high energies. We never directly see atoms. We see the patterns in their light spectra. We never directly saw the Higgs field. We saw the Higgs particle it produced when enough energy was concentrated in one place. Indirect detection is legitimate science. It's how we've made most of our greatest discoveries about the fundamental nature of reality. So where does all of this leave us? What is the verdict on Planck stars? Let me give you the most honest and accurate answer I can. Planck stars are a theoretical proposal. They arise from applying the principles of loop quantum gravity to the problem of gravitational collapse inside black holes. The proposal is mathematically rigorous, physically well motivated, and it resolves some of the deepest problems in theoretical physics, including the singularity problem and potentially the information paradox. It makes specific predictions about what happens inside black holes. It suggests that black holes are temporary structures, not permanent ones. It proposes that the singularity is replaced by a bounce at the Planck density, and that black holes eventually transition into white holes, releasing the matter and information that fell in. But Planck stars have not been observed. No experiment has confirmed their existence. No astronomical observation has produced evidence that can only be explained by the Planck star model. The proposal depends on loop quantum gravity being the correct description of quantum gravity, and loop quantum gravity itself has not been experimentally verified. Other approaches to quantum gravity, including string theory and asymptotic safety, offer different pictures of the black hole interior. We do not currently know which approach, if any, is correct. Could Planck stars actually exist? Yes. They are consistent with the fundamental principles of physics. They arise naturally from a well-developed theoretical framework. There is no known observation that rules them out. And the underlying logic that quantum gravitational effect should prevent infinite density is broadly shared across the quantum gravity community. Planck stars are possible. They are plausible. They might be real, but could they turn out to be wrong? Also, yes. Loop quantum gravity might not be the correct description of quantum gravity. The specific mechanism of the bounce might not operate as the models suggest. String theory's fuzzball picture might turn out to be closer to reality, or the truth might be something none of our current theories has imagined. This is the honest state of the science. We have a beautiful theoretical proposal that resolves deep problems. We have potential observational pathways for testing it, but we don't have proof. Not yet. And there's something important about that uncertainty that I think is worth reflecting on. We live in a universe where massive stars collapse and form black holes. This is observed fact. Those black holes contain interiors that our best classical theory, general relativity, describes as singularities, points of infinite density where the laws of physics break down. This prediction is almost certainly wrong, not because general relativity is a bad theory, but because it's a classical theory being pushed into a regime where quantum effects cannot be ignored. Something happens at the center of a black hole, something real and physical. Matter falls inward and reaches extreme conditions. What happens next is one of the deepest questions science has ever asked. And the Planck star proposal, whatever its ultimate fate, represents one of the most thoughtful and carefully constructed answers ever offered. It tells us that the end of gravitational collapse might not be an end at all. It might be a turning point, a moment where the universe, compressed to its most extreme possible state, finds a way through. The matter doesn't vanish into an infinity. It pauses, reverses, and eventually re-emerges. The information isn't destroyed. It's preserved and ultimately released. The black hole isn't a permanent prison. It's a temporary state in a longer process that we're only just beginning to understand. Whether Planck stars turn out to be the correct description of nature, or whether the truth lies elsewhere, the question they address is real and urgent. What happens when matter collapses past the point where classical physics can describe it? What replaces the singularity? What is actually inside a black hole? These questions sit at the intersection of general relativity, quantum mechanics, and our deepest understanding of the nature of space, time, and matter. They are among the most profound questions humans have ever asked. And the fact that we can ask them, the fact that we can formulate precise mathematical models, derive specific predictions, and design observations to test those predictions, is a testament to how far our understanding has come. We are creatures living on a small planet orbiting an ordinary star, and yet we can reach with our minds into the interiors of black holes and ask what happens at the most extreme densities nature allows. The singularity might not be real. The collapse might not continue forever. Something might stop the fall. And if that something is a Planck star, then hidden inside every black hole in the universe, there may be a tiny, impossibly dense, bouncing core of matter undergoing the most extreme physical process in all of nature, waiting for the slow crawl of time to finally let it emerge. We can't see them, we can't prove they're there, but the physics says they're possible. And in a universe full of mysteries, that possibility is worth holding on to. Because every answer we've ever found about the fundamental nature of reality started as a possibility. An idea. A question about what might be real. And sometimes, the questions that seem most impossible to answer are the ones that change everything. Thank you for staying with me through this journey tonight. We've traveled from the heart of a dying star to the smallest meaningful scale in all of physics. We've explored what happens when gravity meets quantum mechanics. We've asked what might replace the singularity, and we've examined an answer that is as elegant as it is unproven. A tiny, transient, bouncing core of matter at the most extreme density nature permits. A Planck star. If you found this exploration meaningful, a like or subscribe would mean a lot. It helps me keep making these deep dives into the most fascinating questions in science. And the next time you look up at the night sky and think about the black holes hiding out there in the darkness, remember what we've discussed tonight. Those black holes might not contain singularities. They might not be the endpoints of gravitational collapse. They might contain, deep inside their event horizons, hidden from all observation, something far more interesting. A quantum gravitational bounce. A turning point. A Planck star. We don't know for certain, not yet. But the universe has surprised us before, and it will surely surprise us again. Good night, and sleep well under the stars.